Okay. So the topic of my presentation is probabilistic data structures, and in order to be able to even explain and go with the presentation forward, we have to explain what are probabilistic data structures. So in a way, they provide a reasonable approximation and an answer of the answer and a way to approximate that answer as well. So that's a very vague sort of description, but it's the best one we got so far. But we might sort of ask ourselves what's the difference between a machine learning model, for example, or a statistical model. So the statistical model tries to explain relationships between groups of variables, and it tries to explain a certain phenomenon. And a probabilistic data structure will not do that most of the time. What it will do is it will transform the data into like a sort of a data model or input model. You can think of this as a technique to reduce dimensionality of the data. And it will then do simple statistical calculations on that data and create sort of simple estimators that we have. So this is the difference. In one way, in models, we try to explain a phenomenon using variables, and in probabilistic data structures, we try to sort of come up with an answer using simple statistics most of the time. All right, so let's move to agenda. So we're going to discuss just a bit more about me and what I'm doing in SDI Media. We have to discuss sets. We're going to do membership tests. So we're going to see how to do a contains operations on sets. Then we're going to move to counting problems. And as a bonus, we're going to do segmentation. So I'm going to show you a model. Well, it's not really a model. I'm going to show you a statistical data structure, which bridges the gap in a way between just probabilistic data structures and models. So this is right in between these two. So let's begin. So I already discussed, who I am and what do I do, but I manage research teams. I'm a performance freak. I still do development. I still do data science. So I'm not just managing people, and just so you know. And what we're doing is we're building a mass scale index amongst other tools, but this is really interesting to our talk here. So we have a lot of problems because you can call it big data. It has just tons and tons of data, and we have to count the data quickly. We have to do membership tests. We have to do distinct counting, and we have to run machine learning models on this gigantic data sets. So this is the example slide of how the application looks like. So you can see we have a bunch of files. They're, of course, artificial files, but we have a bunch of data points. And you can sort of tell that it's artificial because the slide here is just showing 47 million. But the reality is of the situation that we have much, much more to work with. So even here, you can see certain probabilistic data structures in motion, and let me just quickly describe them to you. So this toggle uses a probabilistic data structure. This count uses another probabilistic data structure. This cart uses yet another probabilistic data structure. So there's a lot of these sort of data structures that we use day to day, and hence this lecture exists, because I think you might have value knowing that these data structures even exist. So let's move to sets. So let me now give you a quick task, and let me give you a problem to solve. So how do we check if a number like 8 is present within a set? Well, what we have to do most of the time is we have to write a simple function, for example, contains, where we're going to pass in the set as an array of numbers and an index. And just we're going to use the for each loop and just see if the set if the item is in the set, and that's pretty much it. So that's all good, but the problem is if we have a bigger set, then it's not going to work really, because we're just going to do this forever, and the set is going to be really, really big when we're going to discuss arrays of ints. So there's a better way to represent sets, actually, and they're called bit sets. So a bit set is a different representation of the set. So we're going to have a bit mask now, and if an item is present in a set, we're going to have a 1 under that index. Otherwise, we're going to have 0. So now, when we're going to ask if a number is present within a bit set, what we can do is we can actually do a simple contains operation, which is just a shift left and an end. And as it turns out, the performance of this code is around 2.5 cycles on a modern CPU. And if we're on a good compiler, like C++, for example, like highly optimized compiler, it's going to use the BTS instruction, which is a hardware instruction to manage sets, bit sets pretty much. So it's going to go even faster. So you can do just large volumes of data using these bit sets. And for our purposes, the real use case is that this set now is 2 bytes long instead of 16 bytes long. So that's quite the reduction of space. And that's all good, and we use bit sets, but bit sets have their problems. So one of the problems of bit sets is that if you have just a couple of numbers, like 1, 500, 8,000, and 1 million, then you have a lot of gaps in between these numbers. So this set is actually 13 kilobytes long, although it contains only 4 items. So we have to solve this problem somehow. And what we can do, there's a couple of interesting ways we can approach this. So the first obvious thing is the compression. We can use a idea that's called run length encoding, for example, which will then take ones and zeros, and it will just count them and note their position. But the problem with that is, and of course, we can use like more advanced data structures. For example, roaring bitmaps are the state-of-the-art data structures in set compression. But all of them work well if you have a bunch of ones and zeros, and you don't have a thing we can call a uniform distribution. So you don't have a big groups of ones and zeros continuously. And if you have that situation, you cannot compress efficiently. But you can still solve the problem using a probabilistic data structure, for example. So one of the interesting probabilistic data structures solve our membership test data structures. So if we have a set, then we're trying to check if an item is within that set. So that's the membership test for you. So one of the most interesting data structures that deal with memberships is the Bloom filter. So a Bloom filter is a different idea of a bit set, because it's a way, it will use a smaller bit mask, but now in order to be able to sort of incorporate more data on a smaller mask, what we have to do is we have to introduce hash functions. And hash functions provide a functionality of semi-randomness. So what we're trying to do now is we're trying to have a uniform distribution of hash functions. So we're going to take the number, for example, 1 here, and we're going to use, for example, 3 hash functions. And these 3 hash functions will tell us the indexes of which we should toggle the 1. So it's here, for example, the second is here, and the third is here. And now we can have overlaps in our numbers, and that's all fine, because when we're going to check if the number is present within the set, we're just concerned in the ones at these locations. So if you're trying to check, for example, if 1 is present, then we take the 1, we use the 3 hash functions that we have in this data structure, and if they all turn up to be 1, well, the item is present within the set. But there's a problem, and you might see it just, popping up its head. So the problem is that if this mask is relatively small and we have a large pool of numbers here, then they're all going to be set to 1 eventually. And then the problem is that if we have an item which isn't the part of the set, for example, like 50 here, then it's going to hash to 1s no matter what. So we can have a false positive. So this data structure can have false positives. So in order to be able to combat this problem, what we have to do is we have to calculate the error rate and the optimal sort of number of hash functions. So usually what you do is you have these 3 formulas, which is the probability of false positives, the optimal number of bits, and the optimal number of hash functions. But they're sort of written in a form of variables where we have to plug the expected error rate and the capacity. So how many items are we planning to even encode on this bit mask? And the really interesting thing about Bloom filters is when they first were written like 25 years ago, something like that, the original paper had a bug in the formulas because it assumed independence. of these ones on that mask. And it was used with success for many, many years in the database system that you use today, in NoSQL systems, in the caches that you use today, probably in the cloud. And no one have any idea that there's a bug in that formula. So the interesting thing happened that a bunch of people a couple of years ago found that, and they proposed a different sort of solution to that, and these formulas were changed. And it was still good, although you have to have a bigger mask. And now, if I recall correctly, there's still some discussions that these formulas can be still improved. So we're going to see how it turns out. So this data structure is very simple in like code, because it's around 50 lines of code, but the mathematics and statistics that come into this data structure is really, really complicated. So let me show you some code perhaps. And let's go to the Bloom filter example. Let's make stuff just a tiny bit bigger. So let me show you the Bloom filter. Let me show you the procedure, but let me show you the data structure first. So this is our data structure. It's super, super simple. We're going to use the bit set that we sort of defined in one of the slides. So our bit set is just an array of longs, because we can have a big bit set. And these are the formulas to add and do contains on our bit set. As you can see, they're super, super simple. So there's not much to talk about really here. And if we're going to go to the Bloom filter, then what you're going to see is that we have two parameters that we have to set. The first one is the capacity. The second one is the error rate. So if we want to compute the M, which is the mask size, and K hash functions, we have to use the formulas that were provided on the slide. And if we plug it into these formulas, we're going to end up with the best possible M and the best possible K. So once we have that, we can add an item. So the thing with the Bloom filter is that if we have to use a bunch of hash functions, it would be good that they have to be sort of pairwise independent. It would be good that they have a uniform distribution. And it would be good that, well, if they're not correlated within each other, for example. So, and as a bonus, for example, which can be proven, well, it's not said anywhere, but you can prove that if you use the data structure, it would be good that these hash functions would be from a different family. So one would be a twister, the second one will do something else. So that's a requirement as well. So it's a lot of hash functions, and you have to be very creative to come up with these hash functions. So we can use a trick. So there's a hashing trick that we can use here. So we're going to do just two hash functions, the primary and secondary hash function. And now when we're going to go to compute the hash and use our hash functions, we're going to generate new hash functions. So it turns out that there's a really clever technique that Dillinger and Malnois invented, and it's called double hashing, where the hash can be represented as a primary hash plus the secondary hash times the index of the hash function. And that's going to generate a pretty good new hash function. So we can use this to compute as many hash functions as we like. But the requirements now are that these two primary hash functions better be good, because if they're not good, then we're going to end up with problems. But we can still use this technique. It has been empirically proven that it works. So you can sort of bet your money that it's going to work correctly. So now, if we have these hash functions, we compute a bunch of hashes and we toggle a bunch of bits that provide the hash provides the index where to set the one on the bit. And that's pretty much it. That's the whole add function. And the contains function is pretty much the same. We have our hashing trick. So primary and secondary hash functions have to be computed. We compute new hash functions and we do the contains operation. So if all of the items are set to 1, then we conclude that, well, the item is within the set. If even one is not, then conclude that it doesn't belong to the set. And that's the whole function. So that's the whole filter. It's like 50 lines of code. No big deal. So as you can see, this is very simple, but in a way it's very complex because there has to be a lot of sort of preconditions met in order for it to even work. So now let's do the test. I have my capacity, which is the expected number of items, set to 150. The error rate is 1%. And here's what we're going to do. We're going to add 100 items to the Bloom filter. Then we're going to ask for 100 items. They should be there. And then we're going to check if we have another 100 items which aren't part of the set, and we know that, but we're trying to compute the false positive rate. So the error rate is going to get computed. So let's run this program and let's see how it's going to perform. Compile. Okay, so we found 100 items, as you can hopefully see. So that's good. Okay, false positives. We have a couple of false positives. So the actual error rate is around 6%. Now, you might ask yourself, well, I just said that it's 1%. It should be 1%, but it's 6. What's up? Well, the reason for this is that, first of all, this is the expected error rate. So this is the best possible error rate, really. You can think of it as the best possible error rate that you can get. You're not going to get any better than this. You can get much worse than this, actually. So that's the first thing to look for. And the second thing is that you have to have your hash functions really robust. So I use very simple hash functions, and you have to use the best hash functions that you possibly can find in order for it to be true. But it's still, even if you don't use like perfect hash functions, like the state-of-the-art hash functions, you still have to be in the ballpark. So 6% is not bad. And if we increase the capacity or error rate, the false positive rate is going to go down to 0 in this example. So that's really good. So all in all, to summarize this this topic about Bloom filters, you use Bloom filters in order to be able to decrease the amount of memory that you use. You don't use Bloom filters pretty much to actually optimize something. You don't do it for performance. You do it for the reasons that you have a lot of data and you have to decrease the memory footprint. Because if you sort of intuitively think about, if you want to have your sets to go as fast as possible, the Bloom filter is a terrible data structure for it. And let me explain, because this isn't explained anywhere on the internet. You have to sort of figure out yourself. So the problem is that, like I said, the hash functions have to be uniformly distributed. That means they're like random numbers. They don't group in any part of the mask, and this is what we want. But if the mask is big, we're going to incur a lot of, and I mean a lot of, cache misses from L1 to L2, because we have to jump through cache lines. So that's not good if we're trying to achieve super high performance. If you want to achieve super high performance, my tip would be to not use Bloom filters, but use a different data structure called a hash table with open addressing, which means you cannot use the .NET implementation because it's not open addressing, it's separate chaining. So the open addressing means if you have a collision, then you look for an open slot around this item. So you go down and you go up, because you're going to end up in the same cache line. And that's what you do if you have to have super fast performance. So you use Bloom filters pretty much to decrease the amount of memory. Okay, moving on. Let's go to the counting problem now, and this is an interesting one. We have a lot of counting problems to solve. So let me again ask you a question. How many times each number is present within this list? So let's count them. So let's figure out a simple procedure. Let's do a dictionary. The key would be the number and the value would be the count. So we're going to go through each item and add or increment. And the time complexity is probably something around ON, and the space complexity, Wikipedia would tell you it's probably around ON, but that's a lie. It's not around ON, because if you think sort of how dictionary works, it's a big array. It's actually two arrays, and one of the arrays has a struct in it, which uses the separate chaining technique. So it's like a linked list within a single array. So the array is big, the data structure is big, the data is big, so you don't end up with ON, you end up with something bigger, but that's fine. So how do we attack this problem in a different way? what we can do is we can use a technique called Countment Sketch. So a Countment Sketch is a similar technique to what we used before, because we're going to use hash functions. We're not going to use bit masks now. We're going to use regular arrays, and we're going to create a matrix of just numbers. So it's a matrix of like rows and columns, and on each row we're going to use a different hash function. So in this example here, we're going to use 4 hash functions, and we're going to hash all of our items using these 4 hash functions. And now, if you're trying to check how many times 1 was present within this list, we take the 1, we hash it here in the first. It's going to end up here, then it's going to end up here, end up here, and end up here. And what we have to do is we have to keep track of the minimum number in each bucket. So the minimum number of all of these rows is 3. So how many times 1 was present in the set? Well, it was present 3 times. And intuitively, if you don't know how this works, is that on each level, you're hoping for a situation where your item will hash exclusively to the same bucket. So no other item will hash to the same bucket. And if it's going to hash to the same bucket, you're hoping for the difference, the error rate, to be relatively small. So that's why you use a couple of rows, because on each row you have a probability of being exclusive in that row. And that's the way that you solve this problem. So the time complexity is O(n), the time to do the count is O from D, because we have to count each row, and the space complexity is OW times D, which is very tiny, and we're gonna see some benchmarks that prove that. So okay, let me go to the demo, but let me just say one thing which is very important for this data structure. So these counts, you can sort of tell that intuitively as well, can overestimate but never underestimate. And if you followed along, then you might know why, because the construction of hash functions will not allow to overestimate unless you're doing something wrong completely. But this is a very interesting property that we can sort of use, and if we know that it exists, it's going to help us later. So let's move to the demo. So let me get out of this example and let's move to this example now. So I have my Countment Sketch here, and this is an even simple data structure. So we have to estimate the W and the D. Again, we have 2 parameters. First is error rate, which is the error rate of the entire matrix. So how of all numbers are. And then we have a certainty, which certainty provides a how certain are we that this count for the single number is correct. So you can think of these two as estimating the W and estimating the D parameters, pretty much. And now we have just 2 methods. Again, we have the increment. When we're going to use the hashing trick, we're going to just end up with a single hash for each row. We're going to increment the counter, and that's pretty much it. That's the whole method, to increment. And now we're going to get the counts. So the counts is, again, pretty much very simple, but now we have to track the minimal number from each row. And if we're going to find the minimum number, then we can solve the problem and we can return the minimum number. That's the whole data structure. Okay, so let's now move to our sort of test procedure. And we're going to set the error rate to 1% and certainty to 90%. And we're going to do like 32,000 items. We're going to have a random array of 32,000 numbers, but we're going to just have 10 buckets. So 10 unique numbers. So from 0 to 10, we can go from 0 to actually 9. So let's run it and let's see how many mistakes we've made. So the row size is 200 and we have 4 rows in this data structure. And as you can see, we got all of them correctly. So there's no errors here. So let's increase that to 100 now. Because you have to remember, the more unique numbers we have, the bigger the data structure has to be in a way, because now we have to have bigger masks on each row. or we have to have like deeper, use more hash functions. So it's one or the other, but let's see how many mistakes we've made here. None. We're pretty good. We're pretty good. So no mistakes still. Let's go up a notch and let's increase this to 1000. So now, as you can see, let me stop it. We're all over the place. So that would mean that we have to decrease the error rate or increase the certainty, and the data structure would work correctly again. So it's a balancing act pretty much. So if you know that you don't have a lot of different sort of numbers, your numbers range from 0 to 100, for example, or if you have just like, I don't know, 1000 categories, then this data structure is extremely effective, because you can have billions of numbers and it's gonna just use like 1 kilobyte of data for counting 1 billion numbers of like different sort of sizes, right? So it's very good, and this is the primary use case of this data structure. All right, so let's move on, and let me now introduce you to my favorite, I guess, problems. So distinct counting problems. So again, let me ask you this. So how many unique items are in this list? And well, we don't know. We have to write something. So we can write a count distinct function where we're going to use a hash set, and our hash set, then we're gonna use our hash set to get the counts, and that's going to be the unique count. So again, space and time complexity is ON. Actually, space complexity is much bigger than ON, but that's good. So you might wonder now, what's the problem here? Well, first of all, counting distinct things is extremely hard. So it's extremely hard on large data sets. And if you ever used LINQ and did like .distinct or SQL distinct, you're going to appreciate how hard it is, because you can wait for minutes at a time to compute that. So that's a problem that we have to solve. And if you're trying to come up with a normal data structure to just call these distinct counts, that's impossible, because you can have multiple different queries that can be distinct. So that's another problem. So and even if you have multiple like numbers and different queries, then that still kind of doesn't work, because there's a lot of data that you have to keep track of, and it's not going to work. It's going to collapse very fast. So let's find a better way to solve this problem. So one of the interesting things that you can discover is that if you have this list and you're going to compute a hash, like a single hash function on it, then if you sort of count the leading zeros of that hash function, you're going to see that something interesting happens. So if we're going to take these numbers into a table and just compute a hash function and count the leading zeros. So 1 has 3 zeros, 5 has 1 zero, 8 has 1 zero, 11 has 0 zeros, and 22 has 2 zeros. If we're going to take the highest number of leading zeros, which is 3 here, and we're going to plug it into this formula here, 2 to the power of leading zeros, we're going to end up with 8. So how many items do we have? We have 5 unique numbers, and this turned out to be 8. You can sort of intuitively tell probably that it's going to work. So this approximation is working. And you can sort of intuitively tell why. Because if a hash function is a representation of a random number in a way, so if we output random bits, a completely random bits, then the probability of getting like k leading zeros will be 2 to the power of minus k. You can sort of figure it out that this is true. And that means that we can come up with a data structure which will solve our problem using just minimal amounts of memory. And of course, it's going to have errors, but for the bigger your data set is, the error should decrease, hopefully. So that's one of the things that we can do. And what sort of things can we do to decrease the error? Well, again, let's compute multiple hash functions. That could work. Let's average them out then, and then hopefully we're going to get a better result. Well, the authors of the original paper thought, well, computing multiple hash functions is kind of expensive, and we don't want that. So maybe let's do the following. Let's change it up. Let's have an array which will track the highest number of leading zeros, and let's hash the items and let's put them into this array. So how do we put them into this array? So we're going to use a different hashing trick this time around. So we're going to split the number of the hash functions, which is 32-bit, into like 5 to 7 leading bits, and then we're going to count these, and the rest of the bits we're going to use as an index in this sort of array here. So now we can have collisions, and the collisions will overwrite these buckets here, but we're still going to track the highest number of leading zeros. But now what we're going to do, we're going to average them out. So when we do this calculation, we're going to average that. We're going to change our formula to this sort of formula. So alpha times the hash size, which is 32-bit, times 2 to the average of m. So that should provide hopefully better results. And alpha is a puzzling thing here, which is the correction factor. So it has been sort of proven that this is a right skew distribution. So you have to have certain things to combat this problem. And alpha was invented, and it's a number which will sort of serve as a correction factor to our counts. So that's one of the data structures, but this data structure is really old and no one uses it because it doesn't provide you with a good approximation. Still, it was great for its time, but better data structures exist. So what we can do is we can use a data structure called hyperloglog, which is pretty much the same data structure, but the core difference of this data structure is that we're going to use a harmonic mean over this array. And we're going to use a slightly different correction factor. And these counts will be different for different sort of hash sizes, so for different items. So we're going to calculate how many items approximately can we have and pick the different formula each time, which is going to be this formula, but with slightly changed parameters. So now hyperloglog can scale into small sets and up to a gigantic sets. And the bigger the set you have, the smaller the error rate is. And the error rate, expected error rate, is around 0.2% for 1 billion numbers, which is awesome if you can think about it. So we can scale to billions and trillions of numbers easily. Okay, so let's go to the demo. And let me show you again this thing count. And what we're going to do is we're going to do a really cool thing. So we're going to have a random array of 1 million elements. Again, we're going to start with 10 unique elements. So 10 distinct elements. We're going to take the loglog and hyperloglog, and then we're going to do the exact counting as well. And we're going to just see how many exactly items do we have, how many loglog predicted, and how many hyperloglog predicted, and we're going to compute the error rate each time we do it. So let's start with 10. So for 10 numbers, loglog predicted 38, hyperloglog predicted 4. So the error rate is 74% versus 54%. And the reason is that I'm not using a hyperloglog, which uses this sort of function to smooth out small counts. So that's on me that it got it so wrong, but let's continue and let's add up these numbers. So we started with 10 unique. Let's go to 100 unique. So as you can see, the error starts to go down. So hyperloglog is at 34%. Loglog is at 34% and hyperloglog is at 19%. Let's keep going down. So 1000 now. Hyperloglog is around 10%. And loglog actually increased, which is puzzling, right? So why loglog increased and hyperloglog didn't? Well, as you can see, harmonic mean is a very effective technique, first of all. And second of all, what we're going to have here is that the hash function construction is, again, very important. And I use the simplest one I can find. So loglog is very sensitive to that, and hyperloglog kind of doesn't care. So that's why. So 10,000 now. So for 10,000, loglog starts to decrease, and hyperloglog is at 8% now. So it's really, really good. Okay, 100,000 now. So for 100,000 approximately, because it's not 100,000 now, loglog still decreased a bit, And hyperlog is awesome, is at 2%. So we can live with 2% for these sort of big counts. No one really cares if you have like a count of 10 million if you got 1 or 2 items wrong. So as you can see, hyperlog is extremely effective at computing the approximate counts of items. Okay, so given all that, let's see how these data structures perform now. So as you can see, this is the add method, and add and contains are pretty much the same in terms of performance for these data structures. So let's compare the Bloom filters. So the Bloom filter is reasonably fast, but it's going to be slower for adding because you might imagine that computing a bunch of hash functions is going to be expensive. But what we're actually trying to figure out is how much memory do we use. So the Bloom filter uses just 170 kilobytes, while our normal data structure, which was the hash set or the dictionary, the hash set, I believe, uses 1700 kilobytes. So it's 17 times the memory used. Now let's move to Countment Sketch, which is an awesome data structure. So our dictionary uses almost 2 megabytes, while Countment Sketch uses 3 kilobytes to represent the same data sets, and even bigger ones. So now let's move to hyperlog and log. So our hash set here is like what? 48 megabytes or 400 megabytes, if I recall correctly. But log and hyperlog are just, and you know, surprise, surprise, 184 bytes. That's like nothing. You can have billions of these data structures counting your stuff in different filters, and no one is going to notice. That's how awesome this data structure is. So again, all of these data structures are designed to, most of the time, decrease the allocated memory, not to be the most efficient ones. So you have to kind of keep that in mind. Okay, so let's move to the bonus round now, which is the data structure that sort of bridges the gap. So let's do the segmentation bit. And again, an interesting problem: how would you split this string here, level up your game, into these words? As you can imagine, it's not easy to do it. So for example, what we could have is we could have a data structure which contains the words and the counts. But as you can see, this data structure is not complete. It's not going to have all of the words, first of all. Second of all, we can have compounds. You and your is kind of a compound word. Hot and hot dog is, again, a compound word. And you have to solve this problem somehow. And as you can see, this doesn't have your, but it still resolves the problem correctly. So this is an example of a data structure which has just a plain data representation like your normal model data structures would have, but it doesn't do anything with the variables. It doesn't try to explain any phenomena. It doesn't try to describe relationships. It does nothing of these sorts. It just uses simple statistics to compute different things. So let's go to the data structure, because it's not from the family of probabilistic in a way, but it's super interesting. So I have my dictionary here, which is like a fake dictionary of a bunch of counts and a bunch of words, level up, game, and you. And we have our input string, level up your game. And we don't have your here. We have you. We would not like to split that. Yep. Yeah, I'm already done. So let's do this example, level up your game. And as you can see, we solved the problem, although we didn't have your. And the construction of this data structure is really, really simple. I'm not going to show you because we're out of time. So thank you. I hope that you enjoyed the presentation. Here's the links to my social media. I run a YouTube channel where I have a different sort of tutorials on low-level programming, performance, memory, and stuff. And you can always follow me on Twitter. So thank you.